Hey everybody, this is the lecture on section 7.1. On parametrically defined curves. And this is in 2 dimensions, and this is a pretty useful concept. And you'll see why in a moment. Given an independent variable t on some interval, a less than or equal to t less than or equal to b, or something like that. A parametrically defined curve, so equations x equal to f of t, y equal to g of t, the set of points xy, the set of points in the xy plane satisfying the fixed equations x equal to f of t, y equal to g of t is called a parametrically defined curve. In 2 dimensions in the xy plane. And here's an example that you have seen before. Okay, say x is equal to cosine t, y is equal to sine t, for 0 less than or equal to t less than or equal to 5 pi over 4. Okay, well, what curve is this? Actually, let's do it like this. X equal to 3 cosine theta, y equal to 3 sine theta. So if you take these points here, or you take the circle of radius 3 centered at the origin, right, so here's x equal to 3, here's y equal to 3, z equal to 0, or y equal to 3, x equal to 0, x equal to minus 3, y equal to 0, and x equal to 0, y equal to minus 3. So now if you take any angle, t, right, so if this is the angle measured in the counterclockwise direction from the positive x-axis, then this point right here, by the definition of sine and cosine, this is the point 3 cosine t, 3 sine t. Okay, at t equal to 0, we would be right here. Cosine of 0 is 1, and sine of 0 is 0. At t equal to pi over 4, we would be right here. At t equal to pi over 2, we would be right there. T equal to pi would be over here. And then at t equal to 5 pi over 4, we would be right here. So what this curve is, this parametrically defined curve, is just this half plus an eighth So 5/8 of a circle. Starting from here and moving in this direction. So as t goes from 0 to 5 pi over 4, we move along this curve to this point. So that's where we start and that's where we end. So the increasing value of t gives a direction along that curve, and the direction is this, counterclockwise direction. Right, and that all just hinges on the fact that, right, the definition of sine and cosine tell us that this point right here with angle t is 3 cosine t, 3 sine t, right there. That's what that point is. Right, and so that's why we get this curve. How about if I did this? Slight variation on that. Oh, notice also in this example that x squared plus y squared is equal to 9 cosine squared t plus 9 sine squared t, which is equal to 9, which of course is the standard equation for the circle of radius 3 centered at the origin. Okay, but we don't get the whole thing, we just get this part, and that comes from analyzing the the domain for t and what points of the curve you get. Here's another example, sort of similar to that. Let's say x is equal to just sine 3t, and y is cosine 3t. And we'll say 0 is less than or equal to t is less than or equal to 2 pi over 3. So this time, right, x squared plus y squared is equal to 1. So we exist along the, let's do a little bit more than that. Let's say 0 is less than or equal to t is less than or equal to pi. Yeah. So x squared plus y squared is equal to 1. So we're lying on the unit circle, the circle of radius 1 in the xy plane. But where do we start this time? Where do we start? Well, at t equal to 0, x is 0, and y is 1. So we start right here. And then as t increases, like as t is equal to pi over 6, for t equal to pi over 6, we're right here. Right? So this time we're moving along the circle in this direction. And how far do we go? Fix that a little bit. How far do we go? Well, we're going in this direction, and we're going all the way out to t equal to pi. But that takes us around the circle, right, a total rotation of 3 pi radians. So 2 pi radians goes from here to here, and then another pi radians goes from here to here. So 1.5 times the circle around the circle in the clockwise direction. Right? Okay, so slight variation on that. And notice, what is the effect of having the 3 here? The effect of having the 3 is that you move faster around the circle, right? Three t rather than 3 is that we move around the circle 3 times as fast. Or rather than t. Oops. The circle 3 times as fast. Okay. So let's put these previous 2 examples together and do something a little bit different. How about this? So describe the motion defined by the parametric equations. So x will do just plain old 2 cosine t plus cosine 6t. Y is equal to 2 sine t plus sine 6t. So what's going on here? Well, I can't square things and then expect to get rid of t. Okay, that's not going to work here. I can't do that same trick. Right, x squared plus y squared is equal to 1, or x squared plus y squared equal to 9. Now that doesn't quite work this time around. Okay, but we do know what these, cosine t, sine t combinations do for x and y. Starting with the circle of radius 2, right, so here's a circle of radius 2. And we'll just say t is bigger than or equal to 0. So at t, right, we have this point here, an angle of t, we have this point here. Right, and then if you take the circle of radius 1 around that, right, so this is the point in the middle here, 2 cosine t, 2 sine t, right? That point is right here in the center of that. But then we're adding to that point cosine 6t plus sine 6t. So that's a circle of radius 1 around this point. And we're going to be somewhere along that. Where exactly, I don't know, but we're somewhere along that. So this is x is 2 cosine t plus cosine 6t. Y is equal to 2 sine t plus sine 6t. Right, so that's this point right here. So that's the point being described. So it's like we're describing a set of points that's moving around this circle, but then you have this thing moving around like that. So it's doing something like this as it goes around the circle. See what I'm doing? I'm pretty sure that most of you have interacted with this kind of motion at least 1 or 2 times in your life. Right? So, I mean, we have this circle of radius 1 that's moving faster That circle of radius 1 is moving faster, and then you're moving around this circle more slowly. So it's doing something like this. Okay, how many loop-de-loops that you make going around the circle once depends on the 6, whether it's 6t or 7t or something like that. But anyway, I took the time to graph it, and this is what you actually get. Or the curve defined is this. See that? So, you know, that kind of motion, if you've ever played with a spirograph toy growing up, you know, if you've ever seen that spirograph, it's those plastic stencils with gears attached to them that you can, you know, put together and do, you know, roll one gear around the other. That's and make designs of this sort. All right, that's one place would have seen it. If you've ever played with that, which a lot of you have, I'm sure. The other place is maybe at Kings Island, right, where they have that ride, the egg beater or the scrambler, I don't know what it's called, where you sit in the basket and it goes in a circle, and then your baskets go in a smaller circle. So that's a fun one. So you know how that feels to move in that kind of motion. And that's, by the way, what the t is. The t is a parameter for time. So what's being described is a certain motion through time. So as time goes forward, we're sort of measuring the motion of this point by doing this parametric curve model here. So that's a much more sort of realistic way of describing motion. In Calc 1, of course, you did a lot of, you spent a lot of time describing motion, displacement, velocity, and acceleration, but the motion was always along a straight line. So here we have something that's a lot more general, not just along a straight line, but along any parametrically defined curve in the two-dimensional plane. Okay, here's some other standard examples. The ellipse. So the ellipse has the following form. X is equal to a cosine t, y is equal to b sine t, and you can say 0 less than or equal to t less than or equal to 2 pi, and you'll notice that x squared over a squared plus y squared over b squared equals 1. Right, so that's the rectangular Cartesian form equation for an ellipse. And this is the parametric equations for an ellipse. And what the curve, parametrically defined curve, looks like, if you have a and minus a on the x-axis, and then b and minus b on the y-axis, then the ellipse looks something like that. Oh, come on. A minus a, b minus b. And again, you're starting here, t equal to 0, and then you're moving around the curve in that direction. So that's an ellipse. It's sort of the idea of like a circle with a variable radius. The radius, has a long part on the a long axis and a short axis, so to speak. All right, so those are ellipses. Another sort of standard parametrically defined, and you can see that it's something a lot simpler than this, right? There's definitely a nicer feel to this set of equations than there is for that. Okay, hyperbolas. So now there's two ways of defining a hyperbola. X is equal to a secant t, y is equal to b tangent t, or x is equal to a tangent t, y is equal to b secant t. All right, so that's two ellipses, or hyperbolas, excuse me. These are the parametric equations for the hyperbolas. And the Cartesian equations, here we have x squared, well, remember, right, sine squared t plus cosine squared t is equal to 1. So when you divide by cosine squared on both sides, you get tangent squared t, right, plus 1 is equal to secant squared t. So secant squared minus tangent squared is 1. Right? Secant squared minus tangent t squared equals 1. So this one is x squared minus y squared, x squared over a squared minus y squared over b squared equal to 1. And then this one is y squared over b squared minus x squared over a squared equals 1. So these are the Cartesian equations. All right, and what do the graphs look like? So you take these points on the x and y axis, b minus b, a and minus a, and you make this rectangle out of it, or square if a is equal to b. And then draw these sort of guidelines through here. Okay. Let me copy that. And this hyperbola, right, when t is equal to 0, x is equal to a, y is equal to 0. So you're at this point here. And this is the motion you get for minus pi over 2 less than t less than pi over 2. And it goes in this direction. And then you also have it over here. Of course, this is not continuous because secant is not continuous at t equal to pi over 2. It's got an infinite discontinuity. So it jumps from here to there. So at t equal to pi, right, secant of pi is negative 1. So you're all the way over here. right, at t equal to -1. And then, or t equal to pi, your way over here, and then you would be moving in which direction? So t equal to pi, so 3 pi over 4. This is negative, that's positive. So you're over here. So this one is moving in this direction as t increases. Actually, I'll leave that part out. We'll just leave this one in. So from minus pi over 2 to pi over 2, you're doing like that. Here, with this one, at t equal to 0, instead of being over here, we're right here. So the parabola opens up this way. Or hyperbola, excuse me, opens up this way. So for this one, at t equal to 0, y is equal to b, and x is equal to 0. So you're right here. And then say for t equal to, pi over 4, the y is positive and the x is positive. So we're moving in this direction. So this is minus pi over 2 less than t less than pi over 2. We're moving along the hyperbola in this direction. So that's a standard curve, this hyperbolic curve, that really has a nicer form when you look at it parametrically than when you look at it in the Cartesian sense. The ellipse and the hyperbola. Okay. How about lines? What do lines look like when you define them parametrically? Well, let's just take an example like this. X is equal to a linear equation with t, say 3t minus 4. And y is also a linear equation with t, 2t plus 1. Right? And we'll just say all t. Okay, well, if we solve for t, let's eliminate the parameter t to obtain a Cartesian equation for the curve. That is an equation with just x's and y's. All right, so let's eliminate the parameter t. We'll start by solving for t over here. So 1/3 x plus 4 is equal to t. But that's also y minus 1, right? 1/2 y minus 1. Right, so we've solved for t in both of those parametric equations and just set them equal to each other, and now we have an equation for x and y. Right, so 2x plus 4 is equal to 3y minus 1. So we've got 8 plus 3, which is 11, is equal to minus 2x plus 3y, right, which is a line. All right, not in y equals mx plus b form, although you could put it in y equals mx plus b form if you want. Okay? So that's a line, and you could draw the graph of that, if you wish, by finding the x-intercept and the y-intercept. Let's look at a couple other examples, and that'll be sufficient for this section. Eliminate the parameter t. Sketch the curve and use arrows to indicate the direction for t increasing. So we'll say x is equal to 1 over square root t plus 1, and y is equal to just t over t plus 1, and we'll say t is bigger than negative 1. All right, so here's my Cartesian equations. All right, how would I eliminate the parameter t? Well, in this one, I can solve x. I can solve for t in terms of x. So here, x squared is 1 over t plus 1. All right, so t plus 1 is 1 over x squared. So t is 1 over x squared minus 1. Right, and then y is equal to, well, it's 1 over t plus 1 times t. Right, I know what t is in terms of x, and I know what 1 over t plus 1 is in terms of x. So y is equal to, well, this is x squared, and this is this expression here, 1 over x squared minus 1. So y is equal to, well, it's just 1 minus x squared. For t's bigger than negative 1, of course, because we have a discontinuity in this and in this, when t is equal to negative 1. We'll have an infinite discontinuity, or something like that. Okay, so, well, this is a standard parabola, but we need to analyze in which direction and what part of the parabola we're using. So here's the parabola. Okay, experiencing some technical difficulties. All right, so we have this parabola, y equals 1 minus x squared. For t equal to 0, we're here. For t equal to 3, we're here. And then for negative values of t, say, t equal to negative 1/2. The y value at t equal to negative 1/2, well, this is negative and this is positive. So we're negative, we're down here. So the movement along the curve coming from t equal to negative 1 is to go from here, and then we hit t equal to 0, and then as t goes towards infinity, we move very, very slowly up to here, where we never quite reach the point where y is equal to 1 and x is equal to 0. So as t goes to infinity, x goes to 0, and y goes to 1. So we're working up to this point, and this part of the parabola never actually gets touched, right, because the x is always positive. All right, one last example. X is natural log 5t. Y is natural log t squared for t greater than 0. Okay, we write x is natural log t plus natural log 5, because that's a product. And then y is 2 natural log of t. We bring down the square exponent for the t. Multiply this by 2. So 2x is 2 natural log t plus 2 natural log 5. Therefore, well, this is y. So y is equal to 2x minus 2 natural log of 5. 2 natural log of 5 is natural log of 5 squared, so that's natural log of 25. All right, so that's just a line whose y-intercept is negative natural log of 25. All right, and then as x gets close to 0, x and y get close to negative infinity. So that's down here. So as t increases from 0, we're moving along the line in this direction. And actually, we get the whole line. Okay, so that is the lecture for this section.